In this video, we're going to see how row reduction operations are related to the determinant of a matrix. So what we're going to start with is just looking at 2x2 matrices. We're going to apply row reduction moves and see how our determinants change. So our first row reduction move that we're going to try out is swapping two rows. So if we have the matrix A, B, C, D, and we swap row 1 and row 2, we end up with the matrix C, D, A, B. And let's see what happens to our determinant. We start with determinant A, D, minus B, C, and after swapping, our determinant is B, C, minus A, D. So the effect was we multiply our determinant by -1. Next, we're going to try multiplying a row by a scalar k. So our matrix A, B, C, D is going to turn into Ka, Kb, Cd. And let's see what happens to our determinant. We start with determinant AD minus BC, and we arrive at determinant KAD minus KBC. Our effect was that we multiplied the determinant by k. Our final row reduction move is replacing a row with that row plus a multiple of another row. So in our example, we're going to have A plus KC, B plus KD, CD. And let's take a look at what happens with our determinants. We start out with AD minus BC, and we end up with A plus KC times D minus B plus KD times C. Let's multiply this out. We get AD plus KCD minus BC minus KDC. Okay. Notice this multiplication is just a rearrangement, and it doesn't matter what order we multiply numbers, we get the same result. So this ends up, these two end up canceling each other, and we get AD minus BC. So there's no change. All right, we're going to try using this to find a determinant without needing to go through the cofactor expansion. We're going to solve the following system just with our normal method of row reduction, and then we're going to look through our work and use that to figure out the determinant of our matrix. So this technique of finding the determinant can be helpful because it lets us work it out without having to do extra calculations. Okay, so all we're going to do is just carefully record our steps as we are progressing through the row reduction. So I'm going to start off by subtracting multiples of row 1 from rows 2 and row 3. Remember that that doesn't change the determinant. All right, so next up, let's multiply row 2 by 1/3. So we're going to take row 2 and go to 1/3 times row 2. The effect on the determinant is that it's going to multiply it by 1/3. So if we started out having determinant of A, we're going to end up with 1/3 times determinant of A. All right, next up, we're going to, let's also scale row 3 by -6. So let's replace row 3 with -1/6 row 3. The effect on the determinant is, again, just multiplying by -1/6. So in total, that means that our new determinant now is going to be -1/18 of our original determinant. Okay, next up, let's take row 2. Let's replace row 3 with row 3 minus row 2. Okay, so as you remember, this is not going to change our determinant. So we get 0, 0, -1, -2. So correction, that last value should be, it'll be 2 minus -2. This should be 4. Feeling a little sleepy today. Okay, and what did it do to the determinant? There was no change. So we're left at -1/8 times the determinant of A. Okay, so let's see, we can multiply row 3 by -1 if we wish to. That gives us 0, 0, 1, -4. Because we took row 3 and we replaced it with negative row 3. All right, and now we're ready to do some back substitution to find our solution. At this point, it is easy for us to write out what our determinant is going to be. If we expanded using a cofactor expansion along the first column, we would see that our determinant is equal to 1. But let's continue on row reducing so that we can find our solution. Okay, so we're going to replace row 2 with row 2 minus row 3 and row 1 with row 1 minus 3 row 3. No effect on the determinant. Here we had 1/18 the determinant of A. Okay, right. Last but not least, we're going to take row 2. Oh, we're going to subtract 2 copies of row 2 from row 1. Again, this is not going to change our determinant. It's still 1/18 determinant of A. All right, and now we have arrived at the identity matrix on the left-hand side. We see our solution. Our solution is going to be x equals -10, y equals 2, z equals -4. So our solution is -10, 2, -4. And let's calculate the determinant of this guy. We've got 1 times the determinant of this minor. So this is going to be 1 times 1 minus 0. So we end up with a determinant of 1. So 1/18 times the determinant of A is equal to 1. So the determinant of A is equal to 18. Now, I know this took a while, but these sorts of calculations are really common to be doing as you're going along. Anytime we are taking a linear combination like this, where we replace a row with the row plus a scalar multiple of another one, we don't see any change. The only ones that we need to keep track of are swaps and where we are multiplying a row by a constant. So these are this can be an easy way to track determinants as we are solving another problem. Okay, so you might look at our results about the relationship between row reduction and the determinant and follow the work, but still feel unsatisfied. So far, our justification has been based on the formula for the determinant. But I think it's also helpful to think about it in terms of the perspective of geometry. The one thing that we're going to use is that the determinant of A times B is equal to the determinant of A times the determinant of B. And I wanted to justify this, probably for the second time. Okay, so we've seen that the determinant is the factor by which volume is scaled under this map that sends a vector v to the product A times v. So for example, if we start out here with the solid cube omega, which has volume 1, if we send every vector in this cube to its image, what we're producing is this parallelepiped T of omega, which has volume 3. So we started out with something with volume 1. We produced something that has volume 3. So we're going to say that the determinant of A has size 3. The sign is based on orientation of vectors under this map, but the size of the determinant just tells us how much we get scaled. Okay, so where does this formula determinant of AB equals determinant A times determinant B come from? We start out with omega, and we're going to calculate its image, B of omega, by multiplying every vector by the matrix B. Then we're going to multiply each of these vectors by the matrix A, producing AB of omega. What happens to volumes? If we start out with volume 1, the volume gets scaled by determinant of B. So B of omega has volume that's the size of the determinant of B. And then this volume gets scaled again by the size of determinant of A. And when we do these all together, we get that the determinant of AB is equal to the determinant of A times the determinant of B. Okay, so let's see this in action. So here on the left we have our 3 row reduction moves. And the idea here is that row reduction can actually be thought of as just multiplying our matrix on the left by what are called elementary matrices. So for example, if we look at a row swap, if we have the matrix 0, 1, 1, 0 times A, B, C, D, this swaps the 2 rows A, B, C, D, giving us C, D, A, B. And using our determinant rule, we can calculate this determinant. We've got 0 minus 1. This is determinant negative 1. This is determinant of A. So our new matrix has determinant that is negative 1 times our original determinant. To multiply a row by k, the elementary matrix that we have is just going to be k, 0, 0, 1. And let's look at what the determinant is here. Here, we get that the determinant is equal to k. And here above, I shouldn't have said determinant of negative 1. That doesn't make sense. I should have just said the determinant is negative 1. Okay, so this process means that we're going to multiply by k. And this sort of makes sense if we stretch in one direction by a factor of k. We expect that our volume is going to scale by that factor of k. Okay, and for our final matrix here, we can express this by taking one copy of our first row plus k copies of the second row, and 0 copies of the first row and 1 copy of the second row. Here, our determinant is equal to 1 minus 0, or 1. And so we see that there's no change to our matrix when we do this row reduction move.